In this video, we take a look at a fairly common situation in research studies where we are testing one treatment against another treatment. In this case, two different medicines for treating hypertension. And mimicking the setup this week that is in the assignment, I've got 20 patients, 10 of whom are being given the one treatment, 10 of whom are being given the other treatment. You can see those 10 here. The average difference is right around 7 to 8 on the systolic blood pressure. This is systolic blood pressure. Their means are high. This is after treatment. We've done an after screening blood pressure. But with just 10 people, we don't have enough of an indication of the difference to prove that the second medication is more effective than the first medication, or that there's any difference at all. And I want to try to show you why. Unfortunately, there's some complicated statistics under this, so I'm going to try approaching it from a more pictorial point of view. Let's take a look at our 10 patients, which we've got here. The blue are those on the first medication. The magenta are those on the other medication. We're hoping to show that the magenta medication is more effective. But as you can see, these vertical columns that you're looking at, those and those are the blood pressures. See across the bottom, there's blood pressures. Those are the blood pressures of the patients on the two different medications. And they're scattered all over the place. You've got blue and magenta all mixed together there. And our mean for the magenta is that 143. It is slightly less. And the mean for the blue is slightly larger. But remember what we're trying to do here. We're taking 10 patients on each medication and then saying, if we expand this to a larger population, that larger population will gain some benefit. We're extrapolating from 10 to an unknown larger population. We're trying to figure out whether the mean for the sample will also be the mean for a larger population. And what these curves, and let me take out the histograms from it, what these two curves mean is this is the possible, underneath these curves, this is the possible range for the population means for the magenta, the second medication, and this is the range of the possible population means. The population being the broader group that we want to talk about. Everybody, say in the FSM, for example, who's got hypertension. And you can see there's a problem here. The two curves overlap, so it's possible that both of these medications actually have the same mean, somewhere between about 142 and up here, this overlap area from about 142 to about 148. So a mean say of around 146 could be true for either medication. Now I'm kind of skimming over things and oversimplifying, but as you haven't had statistics, I'm not going to go into all the details of how we work that out. But think of it as that's where the means could be. And they could be the same if there's someplace between the actual mean is someplace between 142 and 148. Add a few people and that mean could go up or down. So with just 10, we don't have a big enough difference. In fact, our p-value is 0.43. We want this to be smaller than 0.05. If you've had statistics, that's the p-value. We don't have any difference in terms of effect size, how big the difference is. We don't have a difference. There's just too much blurring, the way I think of it, between the two down here in this range right in here, along this here to here. These overlap. And underlying that is the fact that there's variation in the data. There's variation in all data. And here we can see the standard deviations, which are a measure of that variability, that variation, and the standard error of the mean here tell us how much variation there is. What we're really seeing is that But this 152 could be up or down literally by about 18 or more. Plus or minus 18 would be perfectly reasonable. So we can't get a good definitive answer because our sample size is small. What we need to do is to increase our sample size. And so in the world that I'm talking about here, the statistics of hypothesis testing, that's what we're dealing with. We usually have two hypotheses. H sub 0 is the null hypothesis. That's the theory that there's no difference. These two tests here, that there's no difference in these means. Uh, the alternate hypothesis is that there is a difference between the means. Then we have some risks, and this is also what this unit is about this week. We have, that's the Greek letter alpha, first letter of the Greek alphabet. Uh, we use that to stand for a risk of a type 1 false positive error, the risk of rejecting a true null hypothesis. The second letter of the alphabet is beta. These were just picked by statisticians 120 years ago or more. Beta is our risk of a type 2 false negative error. So what do those errors mean? Well, let me pull up a drawing here. Too far. A false positive is called a type 1 error would be in a case like this, where the doctor tells us, man, you're pregnant. That's a false positive. If a pregnancy test comes up positive for this fellow here, that's a definite false positive. That's a type 1 error. Our risk of a type 1 error is referred to as alpha. But the other possibility is a false negative error, like this type 2 false negative error here. The gynecologist telling this woman, don't worry, you're not pregnant. If indeed she is pregnant, that would be a false negative. That's a type 2 error, and our risk of a type 2 error is referred to as beta. So if the null hypothesis is true, there's no difference, and we leave it alone, we fail to reject it, that's the fancy way we say it in statistics, that's the right decision. In other words, we say if it's true, and we say, yeah, we're not going to reject it, it's true, good, we made a decision. If we reject that, we've committed a type 1 error. We've done a false positive error. We've rejected the null hypothesis of no difference when we shouldn't have. And that probability is alpha. If the null hypothesis is indeed false, if there really is a difference, and we fail to detect that difference, that's a type 2 error, probability beta. There may be a real difference in this first two data sets here. That difference might be real, in difference in the means. That's what M is mean. The mean of 152 and the mean of 143. Those differences might be real, but we're going to say, no, we can't prove they're different, they overlap. Well, we may be wrong, and if we're wrong, that's a type 2 false negative error. We have failed to detect a difference when we should. If we take 1 minus our type 2 error, that's referred to as the power of the test. It tells us how powerful our test is. And power is influenced by sample size, how many people you have. If you have a small sample size, as we had back here with this setup here, if you have a small sample size, then you have low power and less likely to detect a difference. If you have a large sample size, that's higher power, more likely to detect a difference. It also depends on the effect size. That's a particular statistical quantity, but it's usually a small effect, medium effect, or large effect. If it's a lower power test, if it's a small effect size, you have a lower power test. If you have a large effect size, you have a higher power test. If the effect size is large, you can sometimes get away with a smaller sample. If the effect size is small, you're definitely going to need a larger sample. And if you have high variability, that always negatively impacts the power of a test. So that's some of the terminology that we use around these things. So let's take our original test. We had 10 patients, and we expand out to 100 patients. So let's do that. You can see that here. I've got these columns go way down off the screen. I've got 100 on the first medication, 100 on the second medication. The means are very close to the original means. 152, this one now 150. 143, 142. Difference, just about 8 between those two. Almost exactly 8. But now, for those who've had statistics, my p-value is way below 0.05. I have a definite difference here. My risk of a type 1 error, very small. And so my effect size, I can do an effect size because I have a difference. It's a medium effect size. So what does that look like back here? Well, here's the histogram. Let me bring that up on screen. And you've still got this overlap between the green and the brown data, but notice there's a whole lot more data points. And that makes a huge difference. I'm going to turn off the histograms so you can see those two giant beams there. That's the spread of the one medication, the possible means, and that's the spread of the other. They do not overlap. They do not overlap. In fact, if I bring them on screen, the one medication, 149 to 150.8, that's its possible range in which it exists. And we come back out to the other one. It's way down here. This one, the population mean, the broader population should see a mean blood pressure of 141 to 142. They no longer overlap. These are statistically significantly different results. Even though the data points appear to overlap, the possible means no longer overlap. The possible means are now separated by a significant amount. And we can be certain, now that we have 100 people involved, that's what's going on here, there's 100 people in both, we can be certain that over a larger population, there is a significant difference in the two medications. And so that's some of the statistical ideas involved in these kinds of studies, where you test one medication against another. And you might initially do a small sample size because that will get you some indication of whether there's any difference to look at all. And that's really common. If you don't get a difference in the small sample size, if these two numbers were the same, you're probably not going to do well to scale up. So we often do a small scale study to see if we've got something worth chasing. And then once we've got something that looks like maybe there's a difference, but our sample size is too small, then we may scale up the sample size and look to see if we can get a significant difference. You can see some of what's happened. This variation of 9 in the standard error of the mean is now down to 1.9. It's dropped by a factor of 9. This is dropped by a factor of 5. So these are much smaller spreads. This is variability. This is a measure of variability. It's much smaller. And so now we've shown that there's a significant difference. Why don't we start off with a big sample size? It's expensive. The bigger your sample, the more time, effort, materials, people working going to be needed. This is 200 blood pressures that have to be taken. The other one was only 20. So whenever you scale up a study in terms of sample size, you're increasing the cost, the time. You may be increasing the risk of certain confounding factors creeping in. Not often a problem with a large sample size, but it can be because you've got to expand out beyond maybe the ideal group that you selected randomly when it was small. You're now maybe going to a convenient sample because it's harder to get people to commit to something. There's a lot of factors involved with scaling up. So you want big sample sizes, but cost, ability to get at the data, it's going to be very, very difficult to do that. You've got to find all those people, get them in, get them measured, and all the other data you have to take. So that's why we don't just automatically run to a large sample size. It just takes too much time. but we depend a lot on public health screening and others to do the daily work to gather the data so we can monitor the population for these sorts of things. And in this case, we'd be starting a blood pressure medication. So that's some of the basics of what you're dealing with in this particular section. And there's some of the things to think about as you're going through this, and the effects they have on your studies that you're doing. A lot of terminology here. There's a lot of good videos online about hypothesis testing, what's a false positive, what's a false negative, and the power of the study. The way I've set this up, I can't tell you the exact value of beta, and alpha is essentially as we say in statistics, a free choice. We usually choose 0.05, but our beta is a bit harder to determine what our probability of a type 2 error is. What we do know is it depends on our choice of alpha among other factors, along with sample size and effect size and other things. I hope this helps. There's a lot of statistics underneath this week's problem. So see what you can do with it, and try to remember these two basic types of errors, false positives and false negatives. Really important, especially if you're working with patients, that they understand that a false positive can happen in a test and a false negative can happen on a test. And so if they get a positive result for some disease, they should not immediately think that things are that they immediately think they have that condition. Follow-up tests will need to be done to confirm it. And even if you take a test and the test comes back negative, it's possible that's a false negative and that you actually have the condition. So with that, see what you can do with this week's homework. Thank you for watching.